Here we go. Groundwater. That's where we're at today. What you don't see, what we can't see. Okay. Rain, it's either going to run off, it's going to evaporate, or it's going to soak in. And so the groundwater we're going to talk about depends a lot on the slope, the vegetation, what kind of soil it is, and how intense the rain was. How much is going to soak into the ground, how much is just going to run off and go to the streams that we've been talking about. A lot of this that soaks in, some of it stays right there at the surface because it's held between the empty pores of either plant roots or soil or whatever. That's a small, small amount. What we're talking about when we talk about groundwater is what it's going to seep down. All of this is going to seep down until it reaches the zone of saturation. Okay, the zone of saturation just is where the groundwater is. The water in that zone is groundwater. So if you've got this hill here, all of this, as the water is running down, this is the zone of saturation where the pores between, whether it's soil or rock, are saturated with water. Above that, you have a zone of aeration where the pores are full of air. Maybe a little bit of water, maybe it's clinging to roots, maybe it's that's right at the surface. So the water table is a fancy name. It's the upper limit for this zone. So right there is the water table. So when you see people talk about the water table's high, the water table's low. The groundwater changes with seasons. It's high in the spring, it's drier in the fall, or lower in the fall. All those things are true. And groundwater changes with topography, where you are, how deep you have to drill a well until you hit water. What are some other things? Porosity, pores. What percent of the rock is actually has open space and pores available? So that's the porosity. It's the percent of the total volume of rock that consists of open pore spaces, whether they're open or filled is separate. Permeability is the ability for fluid to get through a substance. So clay is actually very porous. There are a lot of holes in clay. The problem is they're all super, super tiny. And so its permeability is very, very low. And nothing gets through. Water doesn't get through. If you've got a layer of clay, you can make a bowl and it's watertight. Like it's okay. Clay is not very permeable, but it's very porous. So those two can seem to contradict each other. All right. Groundwater moves back and forth through all the small openings. It's moving slower when the pores are smaller because it's got to trickle through in a line. You can't have all of it going side by side. Okay. You can have pockets of groundwater above the water table. Those are perched or raised water tables. They are usually very, very small. And this down here, C, with that what's labeled C here, has to be impermeable or blocking the water. All right. So a spring. So this is another same setup. I just wanted to show you some more pictures. Here, all the little spaces between the rocks are filled with water. Here, all the spaces below the dotted line are filled with water, but you've got air bubbles in all of this right near the top. That is not saturated. That's water still trickling down. Just trickles down slowly. All right. Same kind of situation. You can have a well, a spring, a water table, zone of saturation, aeration. So if you've got a steep slope, if the side of the slope ever meets the water table, you can get a spring where water will rise to the ground. Water doesn't necessarily get pumped up. The ground can cut down faster than the water table does. So it forms when the water table intersects the surface ground surface. It's also the name of the water. The spring is the water that emerges. Let's see. So we got a couple more of these. We're going to talk about wells in a minute. I want to leave that picture for a second. Here's another tale. Same thing. This is a perched water table. All right. This calls it an aquaclude. I've heard aquatard. Anything that's going to slow down or occlude the movement of water below here is going to hold water, which means you have a small water table elevated above this. Okay. Missouri Department of Natural Resources. There's some springs, cold springs. It doesn't have to necessarily bubble up out of the ground. A spring can absolutely run into the bottom or feed a stream. And there are definitely some cold natural springs on the Black River, closer down to Poplar Bluff, or north of Poplar Bluff, and on the White River in North Fork of the White River in southwest Missouri, right on the Arkansas border. Those are natural springs. They're very cold. They're very clean, fresh water, all that kind of stuff. All right. What else? Hot springs. Hot springs around here means Hot Springs, Arkansas. A hot spring is this. You're going to heat this water. As long as it's 6 to 9 degrees Celsius warmer than the average air temperature at that location, it's considered a hot spring. So sometimes hot spring is bathing water, and sometimes hot spring is boiling. Don't get near that. It will scald you water. Okay? There's over 1,000 hot springs in the U.S. As you go deeper in the earth, we think of going down in the basement is getting cold. And we think of digging in the earth. That first few feet are cold. Yes. But as you dig deeper, the temperature is going to go up about 2 degrees Celsius for every 100 meters you dig down. Because the earth is getting warmer as you go down. And so while, yes, near the top, it's cold, right? Summer, winter, it's cold. It's not permafrost in this area, but we've got different surface temperatures. We think of the ground as cold. Down in a mine, way down, temperature starts to go back up. You just got to get past that little initial, and then it's going to go back up. So when the water from down there, it mixes with surface water, you can get hot springs. All right. The color in there is dissolved minerals. All right. All sorts of complex chemistry going on. It's hard to make a big, broad statement about them because every little chemical is dissolving nearby stone. So whatever's in this stone is going to get dissolved by this water, and then that's going to produce some chemical reaction and make all sorts of weird colors. Okay. Mixes with the gases. All right. Geysers. A geyser is an intermittent hot spring, fountain, column of water is forced up and blasted out of the earth. It's very impressive, like really impressive. Geysers don't just exist on Earth. There is a moon out in our solar system, Io. It's a moon of Jupiter, has water, H2O geysers on it. No. It's Io. No, Io is volcanically active. I didn't write that one down. I apologize. There is a liquid H2O geyser all across this moon and our planet, and I'm mixing it up right now. In fact, pause. All right, we're back. I had to look that up. I apologize. Io, the moon of Jupiter, is volcanically active. There are volcanoes all over this thing going around Jupiter, but it's Enceladus over around Saturn. My battery just died and it's not working right now. Yes, I don't want, oh my gosh. Chromebook's dying here. Here we go. Enceladus, this photo right here, shows geysers spewing water, and that water actually contributes to the snow and ice that make the rings of Saturn. This planet has weird pressures inside and it's making a geyser. All right, we don't need to get into all that because that's not geysers on Earth. Geysers on Earth are intermittent. They start, they stop, they start, they stop. All right. What you're going to do is, it is so hot underneath. It's over 100 degrees Celsius down here. So that water wants to boil, but that water is under pressure. So it doesn't boil at 100. It's staying liquid, but it's over 100 degrees. A little bit of water is going to come up. A little bit of water is going to bubble over because it's expanding. So as it expands, it's going to bubble a little over. Now that there's a little less on there, there's less pressure. And when that pressure goes down, all of a sudden, some of that water with less pressure, it's over 100, it starts to boil. And when it makes steam, now all of a sudden the steam expands thousandfold and flies up and out beyond, carrying some of the water with it. And then you wait a second, and within an hour, the pool has refilled with cold water, reheated, and Old Faithful's ready to go again. Used to be every 45 minutes, about every hour now. Kind of depends. It's awesome. I've seen it once. It's really cool. Nice. All right. So that's a geyser. Wells. I left this image up on purpose. 65% of the groundwater in the United States is used for agriculture. In fact, I don't even know if that's a U.S. That's probably applicable worldwide. We irrigate. Center pivot irrigation. I had a friend once. They were looking at something on Google Maps and asked what this weird alien crop circle shape was, and I laughed. They're like, "Why is it brown square in a green perfect circle?" And I said, "That's center pivot irrigation." You can look all across the Midwest and find that. Huge well, big long arm, swinging the whole thing around, watering a whole field. But if we don't give time for that water to refill the aquifer, then we are using water. All right? You can create a zone. This is the drawdown. When you turn the well on and run the pump, whether it's a house or agriculture, this is a drawdown because the water takes time to move. Remember, this isn't just liquid. It's got to move through the dirt, through the rock to get here. That doesn't happen immediately. And so you can get this cone of depression. The drawdown is the amount that it dropped right at the well. The cone of depression is the shape and size of that cone right there. I can't overstate how much we need to take care of the water we've got, whether it's pollution, it's overuse. Aquifers are running dry. I can't even, the news article last 3 weeks ago I was hearing in southern Louisiana, you're like, it's marsh everywhere. They don't even have to drill a well. They just put a pump right there on the ground. Yes, the water table is extremely high in Louisiana, and there is a big, big aquifer there. But the way they're farming rice, they're using more water than is being put back in. And if you leave that aquifer low, salt water intrudes and seeps into the aquifer. Once you get salt water in there, you can't get it out. Because if you keep pumping it up and you start putting that with a little bit of salt water on the crop, kill the crop. You're done. So you got to constantly test to make sure you didn't. There is a limited amount of water on this planet. Yes, it's renewable. It's going to rain. It's going to it's going to run. It's going to evaporate. It's going to do the whole thing. But there's a limited amount of it, and we just need to be careful with it. All right, let's keep going. Caverns and caves. All right, limestone caves. Limestone are crazy features this Earth has. Limestone, basically, you've got carbon dioxide in the air, you rain, so you've got carbonic acid. Carbonic acid dissolves limestone, and you get crazy shapes, stalactites, stalagmites. You've got tubes, all sorts of things, chemistry going on in caves, and it's awesome. Um, I went back to DNR. There are different caves. There are caves in the Ozarks. They've got a drawing. It's a little small. Karst. Now, if you've ever heard of karst, Karst, topography, that just means land or topography shaped by dissolving power of groundwater. So not like the runoff and erosion of groundwater, but by the dissolving of it. So caves, cliff faces, different things. That's what karst topography really is. And Karst in Missouri, Honka State Park. All right. Uh, so there are entire overhangs. There's sheer cliffs and cutouts and caves. There's all sorts of features going on in Honka. It talks about how they do dye tracing to see where this groundwater is, where the spring is coming from and where it's going to, and they track this. All right, last thing for karst topography: sinkholes. South Cape has sinkholes. Sinkholes are around here. Sinkholes are slow. They are hidden. They are subtle, and they can be dangerous. So, because it's not erosion, it's chemical erosion, right? It's chemical erosion. It's not fast moving water that sweeps this out. It's slow erosion, making a hole, making a cave, if you will, underneath something by dissolving it chemically. And then there's just this hole. And then at some point, the top can cave in as the void grows. And there's all sorts of weird stuff going on. So that's a sinkhole. All right, there is an assignment this week. Details, check on Canvas. Everybody, have a great day. I will see you Monday.